Hey guys, welcome back to my channel Study with me. This lecture is for second year students of mechanical engineering. This is the topic of 80, that is applied thermodynamics unit number 1, in which we are going to see the important topics related to it. So first topic is reverse Carnot cycle, that is also called as gas cycle. Now let us see the PV diagram for that. So here it is P and here is V. Accordingly, the first isentropic process takes place, and we give this as the point number 1. While isentropic process, air is compressed isentropically and the pressure increases and volume decreases. In isotropic compression, from 2, again the pressure increases and the volume decreases. After this isentropic compression, the isentropic expansion takes place. So here the pressure decreases with increase in volume as they are inversely proportional, and from the point 4 to 1, again isotropic expansion takes place where the pressure decreases and volume increases. This is the TS diagram, temperature diagram. So here the T1 temperature is equal to T4 temperature, and 3T temperature is equal to T2 temperature. So now this is the figure. Here it is showing point number 1, 2, 3 and 4. Now first point, how it takes place generally, that is the first point, isentropic compression. Isentropics, here air is compressed isentropically. During this process, pressure of air increases and the specific volume decreases, as you can see in the figure. Here there is a rise in pressure and decrease in volume. Now here no heat is absorbed or rejected by the air. Now our second point is isothermal compression process. Isothermal compression process. In this, air is compressed isothermally, that is T2 is equal to T3. This takes place from point number 2 to point number 3, that is here you can see this point number 2 to point number 3. Now isentropic usually means at constant temperature. So here we are seeing that T2 is equal to T3, and here the heat rejected per kg of air during this process is given by this equation. Q of 2 to 3 is equal to T3 S2 minus S1 S2 minus S3, that is also equal to T2 S2 minus S3. Here T3 or T2 can be taken as that the value of T3 and T2 are similar. So now third part, the isentropic expansion process takes place, and now air is expanded isentropically, which release no heat or no absorption of heat takes place. Now our fourth point is isotropic expansion process. Air is expanded isothermally and heat absorbed by the air, or heat extracted from a cold body. During this process, per kg of air is given by this equation. Q of 4 to 1, that is from the figure, this Q of 4 to 1, that is equal to T4 S1 minus S4, that is equal to T4 bracket S2 minus S3, that is also equal to T1 S2 minus S3. Here temperature is constant, so we can take as T1 is equal to T4. Now work done during this cycle per kg of air, the that is given by heat rejected minus heat absorbed, that is equal to Q of 23 minus Q of 41. Now by substituting the following equation number 1 and equation number 2, we get this that is equal to T2 bracket S2 minus S3 minus T1 S2 minus S3. Here S2 minus S3 is common, so we'll take it common out, and we'll be getting T2 minus T1 into S2 minus S3. Now on this page, COP of refrigerator working on reverse Carnot cycle is given by COP of refrigerant is equal to heat absorbed divided by work done, that is equal to Q of 41 divided by Q of 23 minus Q of 41. Now substituting the values from equation number 1 and equation number 2, we will be getting T1 S2 minus S3 divided by T2 minus T1 into S2 minus S3. Here S2 minus S3 divided by S2 minus S3 are common, so we can cancel it out. So now we'll be getting T1 divided by T2 minus T1, that is the difference between temperature. The Carnot refrigerant works on reverse Carnot cycle. A reverse Carnot cycle using air as working medium is shown on PV and TS diagram. Now, factors which affect the COP of the cycle. The COP of reverse Carnot cycle may be improved by decreasing higher temperature, that is the temperature of hot body T2. Here COP can be increased by decreasing this T2 value. This T2 value should be reduced at a smaller quantity, otherwise the equation will again be in negative format. So now our next point is increasing the lower temperature, that is the temperature of cold body T1 also improves COP. Here after increasing T1 there will be increase in COP, as the T1 is in numerator. Now our third point is, although this cycle gives maximum COP, yet it is impossible to achieve this because the isentropic process of the cycle requires high speed, while the isothermal process requires an extremely low speed, which is impractical for the air or gas. So hence this actual COP is less as compared to theoretical COP. Now our next topic is vapor compression cycle. Here this C is the main part, that is compressor. This compressor compresses the air and transfers it to condenser, and this condenser again liquidifies the water vapors and sends to expansion valve, where they are expanded and again transferred to this evaporator, and this is actually evaporator, and this evaporator again transfers it to compression. Here the TS diagram is shown, this TS diagram is shown, and here pH diagram is also drawn. Now the basic of this vapor compression cycle is they are divided into majorly 4 parts: compressor, condenser, expansion valve, and evaporator. Now first point is compressor. Compressor sucks vapor refrigerant from the evaporator and compresses it so that the pressure increases. The basic function of compressor is to compress the air and increase the pressure. Now by increasing the pressure, its condensation temperature increases. As the pressure increases, in turn the temperature also increases as they are proportional to each other. Therefore, by using higher condensation temperature, we achieve condensation, and condensation is achieved by the using atmospheric temperature. Now our next component is condenser. Condenser, after compressors, high temperature and high pressure vapors will go into condenser. In condenser, these high temperature and high pressure vapors are converted into high pressure liquids. Since here vapor are converted into liquid, heat gets rejected to this atmosphere during process 2 dash, that is sensible heat get during this process 2 to 2 dash sensible heat gets rejected, that is temperature drops, and 2 dash to 3 latent heat gets rejected, that is temperature is constant. During this condensation, pressure will remain constant. So see, compressor compresses low temperature and low pressure liquid and transfer it to condenser by converted into high temperature and high pressure vapors, and this condenser liquidifies and converts this into high temperature and high pressure liquids, and this after expansion valve go to evaporator and again converted into converted into low temperature and low pressure. Expansion valve is usually used to convert this high temperature and high pressure liquids into low pressure and low temperature liquids. Now our third component of vapor compression cycle is expansion device. Here it is a expansion valve also. It is also called as expansion valve. Generally for small capacities, capillary tube is used as expansion device. Generally, expansion process is considered as throttling process. During this expansion device, high pressure liquids is expanded to low pressure liquids. As the pressure reduces, boiling point also reduces. Refrigerant now can boil and evaporate at low temperatures. So for small capacities, we uses capillary tubes for expansion, and this is also called as throttling process. As before stated, in expansion valve, the high pressure liquids and high temperature liquids are converted into low pressure and low temperature liquids, so we can achieve less boiling point, and it is easy to transfer. Now our fourth component is evaporator. In evaporator, this low pressure liquid is converted into low pressure vapors. See here, this low pressure liquid is get converted into low pressure vapors. Now this since pressure is low, refrigerant will boil at low temperature. Now during boiling or evaporating, refrigerant will absorb heat and liquid converted into vapors. So from pH and TS diagram, we will be getting work work input is equal to H2 minus H1, that is in kilojoule per kg, and rejected rejected energy is equal to H1 minus H4, that is in kilojoule per kg, and COP of an ideal VCC, that is vapor compression cycle, is H1 minus H4 divided by H2 minus H1, and that is equal to heat absorbed upon compressed work. Also heat rejected in condenser is H2 minus H3, and this M is equal to refrigerating capacity to that of refrigerating effect per kg, and these symbols are written here. Now turning to the next page. Ammonium absorption refrigerating system. This is actually a basic model, but it is very difficult to understand. There is a generator, then this pump, and then cooling tower, weak solution, absorber, evaporator, expansion valve, condenser. These are the basic components of an absorption refrigerating system. Here this heat transfer rate Qg to the generator, and the desired effect is the desired effect in the evaporator heat transfer rate is QE. Here COP of absorption refrigerating system is defined as COP is equal to QE upon QG, that is equal to heat absorbed in the evaporator to that of heat supplied in the generator. You can easily remember this diagram. This diagram also will give you full marks. See, first the condenser. Condenser condenses this cool air the entering from the surrounding and liquefies it. This is actually NH3 model, that is ammonia model. So liquid NH3 gets transferred with high pressure and liquid NH3 into expansion valve. This condenser's function is to increase the pressure and temperature. After entering in expansion valve expands this NH3 and convert it into low pressure and low temperature liquid NH3. After this low temperature and low pressure liquid NH3 transferred to evaporator. Evaporator evaporates this and converts it into low pressure NH3 vapors, and these vapors are transferred to the absorber. This is absorber which is one end is connected to analyzer generator and other end is connected to pump, and this one more end is connected to continuous supply of water. There is here it is entering and exiting. So this solution of NH3 plus H2 will be transferred, and this is a strong NH3 plus H2 solution, and this pumps this strong NH3 and H2 solution into generator. Generator separates this NH3 plus H2O solution, and this H2O solution is again pumped back to the from the pressure reduction valve to the absorber, and this analyzer collects this NH3 plus H2O vapors and transfer it to condenser, which are actually high pressure NH3 vapors, and this cycle goes on again and again. Now comparison between vapor compression cycle and absorption system. Absorption system, compression system. First use of absorption system is use low grade energy like solar exhaust gases, but in compressor system uses high grade energy like mechanical work. Now next point in absorption system, that is the moving parts is only pump, which is a small element of a system, hence smooth operation takes place. But in compression system, moving parts is compressed, which is a major element, more wear and tear and noise occurs. Now third point of absorption system is low COP, and for compression system higher COP is obtained. Now in absorption system, our fourth point is work on lower it can work on lower evaporator pressure without affecting the COP. But in compression system, COP decreases considerably with decrease in evaporator pressure. And absorption systems, last point is liquid traces of refrigerant at the exit of the evaporator consist no danger. But in the case of compression system, the liquid traces in the suction line can cause a much danger or damage to the compressor. Now we are starting with air conditioning. The science and practice of creating a controlled climate in indoor spaces is called air conditioning. A climatic condition in the room is controlled by AC, and it depends on major four factors, that is the temperature, relative humidity, air purity, and air motion. Actually, temperature means heating or cooling effect. Relative humidity means humidification or dehumidifications. And our second last point, purity means filtration, and air motion means proper air velocity. Now moving ahead, psychometry. Psychometry is the study of a property of mixtures of water vapor. Mixtures of water vapor plus air. Psychometric terms are basically dry air, moist air, saturated air, humidity, etc. First, we are studying with dry air. A dry air is air which is free from water vapor, in the air in which water vapor is absent. And moist air, it is the mixture of dry air and water vapors in which water vapors are included. Saturated air, it is a mixture of dry air and water vapors when air has diffused the maximum amount of water vapor into it. Means the air is containing maximum amount of water vapor in it. This type of air is called as saturated air. And humidity and specific humidity or humidity ratio is defined as the mass of the water vapor present in kg per kg of dry air. Now humidity is given by W, that is equal to mass of water vapor to that of mass of dry air, that is equal to mw, m to the base w, and m to the base a. I have denoted it to better recognitions, usually expressed in gram per kg of dry air. Now our next definition is relative humidity. It is the ratio of mass of water vapor present in a given volume at temperature T to the mass of the water vapor present in the saturated air of the same volume at the same temperature. This is denoted by phi, and it is the same as written in the definition: mass of water vapor in the given volume to that of mass of water vapor in a saturated air of same volume and same temperature. Now moving ahead, the other definition from the Google, it is the amount of water vapor present in the air expressed as percentage of amount needed for saturation at the same temperature. Now our next point is degree of saturation. It is the ratio of specific humidity of a moist air at temperature T to that of specific humidity of saturated air at same temperature T. It is denoted by mu, that is equal to W divided by WS. I have denoted this for better remembering. That will be equal to specific humidity of the moist air to that of specific humidity of saturated air. In other words, we can say that the ratio of actual humidity ratio to the humidity ratio of a saturated mixture at the same temperature and same pressure. Now we are starting with dry bulb temperature, that is also denoted as DBT. This dry bulb temperature is very IMP point. You should star mark it. It comes to the exams: dry bulb temperature, wet bulb temperature, and wet bulb depression. These are the IMP points. You should learn them properly. Dry bulb temperature is denoted by dBT. It is the temperature of air recorded by thermometer when it is not affected by moist air. And wet bulb temperature, it is the temperature measured by thermometer when the bulb is surrounded by wet cloth exposed to air. Means it is actually temperature at which the bulb is exposed to atmosphere or moist air. And wet bulb depression, it is the difference between the dry bulb temperature and wet bulb temperature at any point. Mathematically it is given as wet bulb depression is equal to dBT minus WBT. The wet bulb depression indicates the relative humidity of air. It relates relative humidity of air. Lesser the wet bulb depression, more the relative humidity. That means wet bulb depression is inversely proportional to relative humidity. Now moving ahead, this is also a IMP point, dev point temperature, that is denoted by TDP. It is the temperature at which water vapor begins to condensate. This is the temperature at which phase change takes place. Or we can say it is a type of it is condensation process. The temperature at which the water vapors in the air is saturated, in other words. Now the dew point temperature of the air, always the saturated temperature corresponding to partial pressure exerted by the water vapor. Consequently, when the partial pressure exerted by the water vapor is known as dew point temperature of the air, can be determined from the steam table. So here it is a temperature and specific entropy graph. From here temperature initial and temperature final can be known, and at the point A it is a cooling point, and at the point B it is dew point temperature. This is the psychometric relations. Number 1, specific humidity to that of humidity ratio, W. Mathematically, W is equal to mass of water vapor divided by mass of dry air, that is equal to mv by ma. And W is equal to mv divided by ma, that is equal to pv, p to the base v and p to the base a. That is finally equal to W is equal to 0.622 pv by pa. Here we have substituted the ideal gas equation, and we have calculated from mass to the pressure. And here R is equal to R bar upon mole weight, that is R is a constant. For air mole weight, that is equal to 28.9, and for water it is equal to 18. Now moving ahead, specific entropy, that is equal to H is equal to HA plus HV. HA is entropy of dry air, and HV is water vapor entropy. Applying energy balance equation, that is equal to MAH is equal to MAHA plus MVHV. Then H is equal to MA divided by MA into HA plus MV into HV divided by MA. Simply we have divided complete equation by MA, and hence we get H is equal to HA plus WHV. H is equal to entropy of dry air, that is equal to mCp delta T. Here m is 1, and therefore Cp delta T is equal to H. In psychometric, enthalpy is calculated with respect to 0 degree temperature Hence HA is equal to 0.05 into TdB. HV is the enthalpy of water vapor. HV is equal to Hg at 0 degree Celsius to CPV TdB. HV is equal to 2500 plus 1.88 TdB from steam table Hg at 0 degree Celsius. This calculation are calculated from the steam table, and SP enthalpy of moist air, that is H is equal to 1.005 TdB plus W into 2500 plus 1.88 TdB. Now moving ahead, specific heat of moist air Cp, the energy balance equation, we get mCp delta T, that is equal to Ma Cpn delta T plus Mv Cpv delta T. So Cp value can be calculated from the energy balance equations, that is 1.005 plus W into 1.88. Now moving ahead, relative humidity phi is given by phi is equal to mass of water vapor in air divided by mass of water vapor in saturated air. After substituting the value of Mv, that is equal to Pv into V divided by Rv into T divided by PVS of saturated into V divided by RV T. At this is at pressure at constant volume is denoted by PV. Pressure at constant volume. Now phi is given by PV divided by PVS, pressure of pressure at constant volume to that of pressure of constant volume at in saturated air. Here actually we have substituted the ideal gas equation, and thus we have calculated the value of phi. The relative humidity is the ratio of actual water vapor pressure PV in the air to the vapor pressure which would exist in saturated air at the same temperature PVS. Now mixing of air streams. Mixing of air streams at different state is commonly encountered in many processes including air conditioning. Following figure shows the adiabatic mixing to two moist air streams. See, from this inlet 1, this is inlet number 1 and this is inlet number 2. From this inlet number 1, M1 is M1 of mass M, air is coming in the stream, and from this inlet number 2, mass of air coming inletted from this inlet number 2. Now after this coming, they both are coming in one stream, they will be get added, and we will get total mass flowing through, total mass mixing of air stream. Adiabatic mixing of air streams follows following govern equation. Number 1, mass balance, and second one is energy balance. Mass balance is M1 plus M2 is equal to M3, and energy balance is equal to M1H1 plus M2H2 is equal to M3H3. And finally we get M1W1 plus M2W2, that is equal to M3W3. Now we are starting with psychometric chart. Psychometric chart is very important concept from which we can calculate various concepts like WBT, DBT, specific volume, saturated line, relative humidity, DBT, specific humidity, and dew point temperature can be calculated from this psychometric chart. Air conditioning is treating or conditioning of air to after its temperature and moisture content to suit specific requirements. Therefore, it is necessary to know how exactly air behaves when it is subjected to cooling, heating, humidifying, etc. The change occurring in the air as it subjected to these air conditioning processes can be traced and analyzed and predicted through the use of psychometric tables. The psychometric tables function, psychometric table or psychometric chart's main function is to check the air conditioning while cooling, heating and humidification. The tables are more accurate, but the chart is accurate enough for practical purposes and such more easier to use. Once understood, the chart is quite simple to use in spite of uh, innumerable lines and curves that appears on the chart. Here I have drawn a psychometric chart. Here this is the line of WBT and enthalpy lines, and this is a specific volume line. This is a DBT line, and this is a saturated line. This whole curve is a saturated line, and this line, this dash line is a relative humidity line, and this line is specific humidity and dew point temperature line. And from this table you can calculate all these values accordingly at cooling, heating and humidifying temperatures. Now we are dealing with psychometric processes. There are in main 4 psychometric processes. Now we are starting with first, sensible heating. When the air passes over dry surface which is at temperature greater than the inlet air, dry bulb temperature rises. It undergoes sensible heating. During this process, the specific humidity remains constant, but dry bulb temperature rises and approaches that of the surfaces. Here simply air is entering in this chamber from 1 to 2, and as the inlet temperature is greater than outer temperature, the air inletted is at less temperature, and after coming in this coil it it increases its temperature, and when it's outletted it is having higher temperature than the inlet temperature. Here it is graph is shown on. Now amount of heat added is equal to H2 minus H1 kilojoule per kg. Now our next concept is sensible heating. Air undergoes sensible cooling whenever it is passed over a surface that is at a temperature less than the dry bulb temperature of the air but greater than the dew point temperature. During the process, specific humidity remains constant. Simply here also air is entering, but here the temperature is less as compared to inlet, and after air outlet the temperature is low, and mathematically it is given the amount of heat removed is equal to H1 minus H2 kilojoule per kg, and here the graph is shown. Now we are starting with our third point, cooling and dehumidification. Whenever air made to pass over the surface or through spray of water that is at a temperature less than the dew point temperature of the air, condensation of some the water vapor in the air will occur simultaneously with sensible cooling processes. Here inlet temperature is greater than inner temperature, and when air outlet is there the temperature will be reduced, and the amount of heat removed will be given as Ma H1 minus H2 kilojoule, and amount of moisture removed is equal to m into W1 minus W2 kg. Sensible heat removed is equal to H1 minus H2 into m kilojoule, and latent heat removed is equal to, actually this is not H1, it is HA, and latent heat removed is equal to H1 minus HA into m into in kilojoule. Here this is the graph related to cooling and dehumidification. Now sensible heat factor, that is SHF, is given by SH divided by TH, that is equal to sensible heat divided by total heat. Further, now next point, cooling and dehumidification. It's unsaturated air is passed through a spray of continuously recirculated water. The specific humidity will increase while the dry bulb temperature decreases. This is the process of adiabatic saturation or evaporation cooling. Here down the diagram is shown. The air is inletted and the air is outletted, and here the graph is also drawn. Now the constant wet bulb temperature, saturated efficiency or humidifying efficiency is equal to rise in humidity to that of maximum possible rise in humidity, or we can say drop in temperature to that of maximum possible drop in temperature. That is also given by W2 minus W1 divided by W3 minus W1, or we can say TdB1 minus TdB2 completely divided by TdB1 minus TdB3. Thank you guys for watching this video, and this I have written before only because to save the time, and please like, share and subscribe to my channel and show your support. Thank you.